Hello, guys. Good morning. I'm just a second late today. Okay. Alrighty. So the plan is today, like I told you last time, we're doing this unit is kind of a review of some of the things I feel are like really important. And so today we're talking about interpreting graphs, and we already took notes on interpreting graphs, and I was thinking about it, and I thought that instead of taking more notes on it, that I would walk through your homework with you. So that's the plan today. I'm gonna essentially do your homework with you. So if you are able to, you can pull up the, okay, I'm glad you can hear me. You can pull up the math-based assignment and work on it with me. Otherwise, this will be here for when you get to the homework. But I thought that doing the homework questions, there's a lot of good stuff in here, and we'll be able to talk about some of the most important things from interpreting graphs from just doing your homework. So again, I'm just gonna walk you through your homework today. I have the printed out sort of version of this math-based assignment, and it's really like spread out, which is really annoying, but it's okay. We'll get through it. Printing math-based assignments like never goes very well. You have like one of the answers on the next page and a graph split between two pages. It goes badly. Anyhow, hello, good morning, guys. So, again, the plan today is, I don't know if you heard me. The plan today is that we're doing your homework. I'm doing your homework with you. We're going to talk about the questions as we go. And yeah, so feel free to pull up the math base as well to work on it with me. So number one says a man is driving along a highway in a car at a constant speed. After a period of, okay, that's important. He says at a constant speed. We'll talk about that in a second. After a period of time, he decreases his speed because of road work. Which graph best represents the relationship between distance traveled and time taken? So a constant speed always means that basically a constant speed is the same thing as a constant slope, which means in a graph that looks like a straight line. A constant speed means a straight line. So I'm not even going to look at the answers. I'm just going to draw the graph, like a sketch of the graph that would be the right one. A is not the right one. That's the one we can see right now. Because it's a curved line and we're not looking for any curved lines. He says he's going at a constant speed and then he slows down. So both of those are constant speeds. So he's going a fast speed and then he's going to go a slow speed. So it's going to look something like this, where we have a steeper slope and then a less steep slope. Both of them constant, but he does switch between them. So because math-based switches the answers around, like it doesn't help me to tell you which letter it is, but look for a graph that looks like that. Because that's going to be the answer to that one. Constant means it's a straight line. And anytime you're looking at speeds, usually speed is like a slope. So that's a good way to like connect things. This piece is for traffic. I'll just write that. There we go. Okay. Do you see how all of this is just like the answers? So on mine, the answer is D, split between two pages. Okay, number two. The graph shown describes, I don't know how to say that name, Lechalon's distance from home throughout his journey. So this guy, the dude, is on a journey. And I'm noticing that this horizontal, this is time. So that's how long it's taking him, and this is like how far he is from home. So we have a bunch of questions. How far was Lishalon from home when he started driving at 5 a.m.? At 5 a.m., which is right here, time is on the independent axis, he was, the graph is right there, which means he must have been 5, the units are kilometers, 5 kilometers from home. So he was 5 kilometers when he started at 5 a.m. 5 kilometers. I think on MassBase it has the units for you. But how far was he from home by 7 a.m.? So at 7, the graph is way up here, which means he was 30 kilometers from home by 7 a.m. And then it asks how long did he take to rest? And so this one is like, it's not telling us a specific time. So we have to look at the graph to be able to tell where he's taking a rest. Remember that slope is speed. And so what we're looking for is a speed of 0 or a slope of 0, which only happens on this graph. Let me pick a different color. It only happens right here. Do you see that? That horizontal section of the graph is where he has stopped. He's resting, whatever. Something's happening so that he's not moving forward, not going any speed. So how long it's asking, it was from 7 a.m. to 8 a.m., which means it was only an hour that he took to rest. So this is 1 hour. And then there's one more question, but it ended up on the other page for me. Oh, 2 actually. How far did he travel between 7 a.m. and 9 a.m.? So on our graph, we're looking at, let's get a highlighter. We're looking at from 7 a.m. to 9 a.m. We're looking at this section. So when he started at 7 a.m., he was 30 kilometers from home. And at the end of at 9 a.m., he had gone 40 kilometers away from home. And it says how far did he travel between those 2 times, which means that he traveled from 30 kilometers to 40 kilometers away from his home. So that means 10. He went 10 kilometers in that amount of time. Even though, like, half of it he was sitting there resting, so he only actually did 10 kilometers. And then, was Lishalon traveling faster in the first 2 hours or the last 2 hours of his trip? The first 2 hours, there's so much writing on my graph. Picking a different color. Okay, so the first 2 hours from 5 to 7, is that what it means? Yeah. Okay, so from 5 to 7 or from 8 to 10. So from 5 to 7, this section of the graph, he went from 5 kilometers to 30 kilometers. That's the times that we're talking about, the 5 to 7. He started at 5 kilometers and ended at 30 kilometers. So that means he went, in between that time, he went 25 kilometers. And the last 2 hours, he went from 30 kilometers to 50 kilometers, which is only 20 kilometers worth of travel. So he was going faster because that took the same amount of time. He went 25 kilometers in 2 hours and 20 kilometers in 2 hours. You might be able to guess that the fastest one is going to be the 25 kilometers in 2 hours. You can also tell this by how steep the graph is. Notice that the first 2 hours have a little bit of a steeper graph than the last 2 hours. A steeper slope means a faster speed. So he was going faster the first 2 hours. Okay, this homework also has a bunch of these like container filling problems. And when I was looking back at your homework, I noticed that the reason that we're going over this, or part of the reason, is that this homework assignment was one of the lowest scored ones. So I don't know. Anyway, so I wanted to talk a little bit about these like water filling things. I remember that we did this in class with that activity on Desmos. Um, but it's really hard when you can't like have the thing fill for you and mark little places. It's hard to sort of just see it. So I'm going to sort of talk about um, what, like how to do this kind of problem. The first thing that's important is that like a smaller circumference, like a skinnier container. I'm just going to write skinnier container equals faster filling. The reason it fills faster is because it's not going to hold as much water. So if the water is coming at a constant rate, a skinnier container will fill faster than a like broad container. So a faster filling on a graph will be a steeper slope. A steeper slope. A wide container is exactly the opposite. It's going to be a slow fill, which means I guess it's like not as steep slope. What word? I've lost all of my words. I guess I'll just put less steep slope. I don't know. So when I'm doing this in my brain, I'm trying to sort of piece together a graph of what this might look like. I don't like to look at the answers because I don't know, it helps me to kind of just do it myself. So I'm going to make a graph here, and these containers fill first from the bottom. So what I'm going to do is I'm going to just highlight like pieces of this container and then draw my graph in the same color so you know maybe where my brain is coming from here. And then this one looks like a ice cream cone or something. Okay, so that first bit, I know that it's going to be the very first part of this container is the skinniest part of this container. So the very first part of this graph should be the steepest slope. So I'm going to start out with like a steeper slope here, and it's also getting wider. So that means that not only does it start steep, but it starts going less steep. So it starts steep and then it's going to go less steep because it's getting slowly wider. And then on that blue part, it keeps getting wider. So gradually it's getting less and less slopey, steep, right? Less and less steep. And then that last part, the purple part that I have, it's stable. So it's wide, which means that the slope is going to not be very steep. But it also means the slope is going to be continuous. It's not going to change because it's the same width the whole time. So that's the markers I look for. When it's changing, I mean, I'm looking for like a curved line. And when it's not changing, when it's a straight-sided container, it's a constant slope. So this last part, I might have, there you go. There you go. So what we're looking for is sort of a graph that starts steep and gets less steep, and then it gets constant at the end. And you will find that graph in the answers. So I'm just going to write over here, this is like the constant part because it's not, the width is not changing. And then this part that we started with is going to be gradually less steep because it's getting wider as it's going. So hopefully that helps us when there's like a couple of these problems, so we'll get to more. But so on mine, the answer, it's right. Look at this. That's exactly what we drew. Yeah, so mine is the answer E, but yours could be different. Oh, look, good, we have another one. Let me highlight it again. So I'm gonna highlight this whole bottom part the same color because it's constant. Again, the width of the container is not changing, which means that all of this part of the graph is going to be the same slope. So here's my graph. And all of that part, let me just get the right color. All of that part is going to be the same. So I'm just going to draw a line straight. I don't actually know how fast comparatively that is, but we'll be able to tell when we see the answer. So, and then we have this piece that's slowly getting smaller, which means that the slope should be slowly getting steeper because smaller circumference means steeper. So we're gradually getting steeper as we get up the like neck of that bottle. So it's going to be like a curved line like that, slowly getting steeper. And then the last little piece here is a really, really skinny, which means really steep, but it's also tiny. It's like that tiny bit is constant because that's not changing. So this last little piece will be like straight and very steep. So something like that is what we're looking for. So this is constant and steep. This part is getting steeper. And this is constant and not super steep. I don't know if this is helping you. Anyway, so the graph that matches that is this one. It's my last answer. So see, sometimes you can't like see the curve very easily, but that's the one that matches the closest to what we drew. So we're going with it. Okay. Here's some crazy journey graphs. Ken started traveling at 9 a.m. from point A to point B in a straight line. So this is kind of weird because I don't know why somebody would travel in a straight line. Actually, we'll talk about that in a minute. But we just have point A and point B. And Ken is traveling on this straight line between point A and point B. So for the first, like the bottom is time, the independent axis is time again, and then this one is distance, the vertical is distance. So in the first, from 9 a.m. to 10 a.m., he goes quite a distance. He goes like 120 down to, so he's 120 kilometers away from point B. And at the end of that hour, he's only 60, 70 kilometers away from it. So he goes pretty far in that first bit. But then this next bit, he goes back. He goes back 30 kilometers. So just picture a guy going back and forth, sort of. He goes, how far is that? 120 to 70 is 50. So he goes 50 kilometers and then back 30 and then stays there for a little bit. Notice that little plateau. And then he goes forward from 100 to 40 kilometers, that's 60. So it goes 40, 60, forward 60, sorry. rests a little bit, and then goes forward the last little bit towards B. So that's what our visualization is here. We'll talk about the specifics as we go through the questions. But first it asks, how far is point B from point A? Which we only know because he starts at point A, and the point A is 120 kilometers from point B. This little bit is what we're looking at right here. He's 120 feet away from kilometers, I mean, from point B. So they must be 120 kilometers apart. How many hours was Ken's journey from point A to point B? So how long did it take him? We're looking at the bottom here. He started at 9 a.m. and went to 4 p.m., which is 7 hours. So it took him 7 hours. Between what times did Ken travel at the fastest speed? So remember, fastest speed means steepest slope. So we're looking for the steepest slope, which to me, this piece looks like the steepest slope to me. He's going real fast. Between 1:30 and 2, he's going really quickly. And I think that gives you the answers. Yeah, it does. 1:30 to 2 p.m. He's going real fast. And what was Ken's fastest speed in kilometers per hour? So we just figured out where he was going the fastest speed, and it was between 1:30 and 2, which is only 30 minutes. We need to figure out how far he went in 30 minutes to figure out the speed. So we're going to go back to our graph and look at how far it was from this point to this point, which was, he started 100 kilometers away and got to 40 kilometers away, which looks like 60 kilometers to me. So we went 60 kilometers. We went 60 kilometers in 30 minutes. They're looking for kilometers per hour. So if he goes 60 kilometers in 30 minutes, how many kilometers would he go in an hour? In twice as many minutes, he would go twice as much as far. So that means it's 120 kilometers in an hour. 120 kilometers per hour. What was the distance in kilometers traveled by Ken between 1:30 p.m. and 4 p.m.? Between 1:30 is here and 4, so it's basically all of this traveling there. So he started at 100 kilometers away and ended up at point B. So that means he went 100 kilometers in that amount of time. Hopefully that makes sense. 100 kilometers. What is the total distance traveled by Ken from 9 a.m. to 4 p.m.? So you would think that the answer to this question is 120, because that's how far away he started and he ended up at point B. But remember that he went backwards, and we have to factor that in, because that's factored into how far he walked or ran or whatever he's doing. I don't know. So we kind of have to record that going backward in our calculations, and then we'll get the right answer. So first he goes, and I'm just gonna list it in blue here. First, he takes this little first jaunt from 9 to 10. He goes 120 to 70 kilometers was 50 kilometers. He goes 50 kilometers in that first little bit. And then he goes, when he's going backward, he goes 30 kilometers. And then he doesn't do anything for that time he's resting. And then we already know that's 60 kilometers that he went really fast. And then he rested. And then he did The very last bit was 40 kilometers. So now we just add all of that up to see how far he went. So 50 plus 30 plus 60 plus 40 equals 18, 180. I said 18 because I was adding the first digits. 180 kilometers. Hang on. Let me just double check. 120 to 70 was 50, and then 70 to 100 was 30, and then 100 to 40 was 60, and 40 to 0 was 40. Yeah. 180 kilometers was his grand total distance traveled. Okay, sweet. Yeah. Okay, this is number 6. The graph shows the amount of water remaining in a bucket that was initially full before a hole was made in its side. The relationship between the amount of water remaining and the elapsed time can be represented by a linear function. Which of the following functions represents that relationship? So this is a linear function like we talked about last lesson with a slope where the m should be, and then a y-intercept where the b is. So what we're looking for is those two pieces to fill in our function here. So first I'm just going to do slope. Slope, remember, is rise over run, which means that if we're looking for a slope in a graph, we're looking for how far it went vertically. Wait. I'm going to do a different point. I'm going to do this one and this one. It's really easy to do this if there's points where it crosses the graph lines. I would pick those instead of, it might change on yours, so just be careful. So on mine, it's really easy to pick out that they went down this amount, which was 4. 20 to 24 is 4, down 4, and then over 1, 2, 3, 4 lines, which is 16. So the way that we write that, because it's down 4, it's a negative 4. And if it's rise over run, m equals rise over run, it's going to be negative 4 divided by 16, which if you type that into a calculator should be negative 0.25 or 0.25 because it's a fourth. So that's our slope. We got half the problem done already. And then the y-intercept is just where it crosses the y-axis, right there. Y-intercept. And it crosses the y-axis at 24. So B is 24. So without even looking at our answers, we already know what it's going to look like. It's going to be negative 0.025 x plus 24. Okay. Oh, and they switched the variables on us, but that doesn't matter. It's a t instead of a x. But on mine, it's a. Okay. This is number 7. The value of a 5,000 investment at 17% per year with interest compounded annually after n years can be modeled by that function. The table shows the value for the first 7 years of the investment. Which of the following graphs correctly estimates the function? So on yours, it will have the rest of the graph. Mine got cut off because it printed. But what you can do, and this is probably what it's best to do, is that you just look at these points, 1, 5,800. Hang on. 1, 5,850. That's a point. It's coming from this graph. I just rewrote that. Table. It's coming from the table. So 1, 5,850, 2, 6,844. I'm not going to write the 0.5 because on the graph I'm not going to be able to tell. And then 3, it's about 8,000. I don't know what the last number is, but we'll go with it. And that's what you're looking for. You're checking to see. Remember we talked about checking on a graph last time. This isn't going to be linear, but we can still do this check. So we're looking for each of these points to make sure it exists. So I'm just going to draw it on this first graph that I have, and then you can find the one that matches on yours. So 1, 5,850, 1. Oh, that's important. So this says that the vertical axis is in thousands, the value of investment in thousands. So 5,850 is going to be, it's going to be a little bit more than 5,000 and not all the way to 6,000. So this so far looks okay, this first graph. That's going to be like my 5.8-ish. And then number 2 should be at 6.8-ish. Wait, where is 2? Okay. Maybe letter A is the right answer. I don't know. 6.8. And then 3 should be at 8,000, which is right here. Yeah. So all you're doing is checking to make sure that these points exist on the graph. I can't check the rest of them because I don't have the rest of the table. But I am thinking that that's probably the answer because the first 3 checked out. So all you're doing is just checking values on that graph. Yep. Okay, getting there. This graph shows a train's distance from a central station throughout the day. When did the train change direction and start traveling back toward the central station? Okay, let's look at the graph. We have time versus distance again, and the train. Remember that these are like speeds, kind of. So it goes really fast the first hour, and then slower the second 2 hours, and then it peaks here, and then it starts going down in slope, which means it starts going back towards its original point. So it changed direction at that highest point, which is at 12 p.m. That's where it changed direction. At what time did the train stop to change drivers? Remember that we're looking for when it's asking for where it stopped or rested or wasn't going anymore. It's like flat. There's no slope. So right here is where it stopped. Oh, I didn't look. It's at 1 to 2 p.m. I don't know if it's, yeah, it's 1. How far had the train traveled between 12 p.m. and 1 p.m.? From 12 to 1, it traveled from there to there, which is 100 and, let's see, 180. So 100 to 180 is where it went to and from. This is 100. That's 180. So it went 80 kilometers. How far had the train traveled between 10 a.m. and 4 p.m.? Is that the whole thing? No, 10 a.m. and 4 p.m. So from 10, excuse me while I erase my work here. Okay. From 10 to 12, they went from 100 to 180, which is 80 kilometers. And then they went 80 kilometers again, back down to 1 p.m. Then they did nothing from 1 to 2. And then from 2 to 4, they went from 100 to 0. So that's 100 kilometers. So we're looking at 100 plus 80 plus 80. 260 should be. Without doing any calculations, determine between which times the train was traveling fastest. So when it says this, without doing any calculations, we don't actually ever need to do calculations for how fast, because when we're looking at a graph, the fastest is going to be the steepest slope. So we're looking for the steepest slope on our graph, which to me looks like this first bit. That's way steep. This is the only close contender, and they didn't go as far in that hour. So that first from 9 to 10 should be the fastest. There you go. Oh yay, another one of these. So this looks like one of those things that funnel? Yeah, this funnel thing. Gonna do some highlighting again. This bottom part I'm gonna do pink, and then all of this is gradually getting wider. So I know that this first piece is going to be constant because it doesn't change shape, constant. And it's also going to be super steep because it's really tiny. And then the blue part is gradually getting wider, which means that the slope goes from being really steep to really not steep. So steep to not steep. It's going to be curved because it's not a constant, it's changing. So on a graph, that would look like, get my pink back. It would look like really steep for a second, constant, steep, and then, actually I'm going to make that steeper because it's probably really steep on the graph. And then the next piece, it gets from really steep to really not steep, like that. That's kind of what we're looking for. And hey, look. That one looks just like what we drew. Okay, I think this is the last one. Yeah. Two students are walking on a straight walking track and their travel graph is plotted. So remember again that these are speeds and not actually like, this is not like the students are walking in a curve or whatever. They're walking on a walking track and it's just their speed. So the student A has gone a lot further and a lot faster the whole time. And student B, he started out pretty strong and then he kind of petered out and only went about 100 meters in total. Oh, and hey, look, that's like kind of the question. So A is asking how far did student A walk? So we're looking at how far this person got. Looks like they went to 250 meters. So we're going to say that 250 meters. And how many more meters did student A walk than student B during the first 5 minutes? So, okay, the whole thing is 5 minutes. So the first student A walked 250, student B only walked 100. So the difference between that is 150 meters. What is the average speed of student A in meters per minute? And then the next one is about the average speed of student B. So when we're talking about average speed, we actually haven't talked about this probably in a while. When there's like curved graphs like this, a lot of times we don't really care about the instantaneous speed because both students walked really faster at first, and then slowed down. That's why there's that curve. We want to know the average speed, which means we need to figure out how much total distance they walked and how much total time it took them. And then that's where we get the speed. So in 5 minutes, student A walked 250 meters in 5 minutes. And student B walked 100 in 5 minutes. So you can divide that. 25, 2 to 50 divided by 5 is 50, I think. 50. And the units on this is going to be meters per minute, I guess. It's a weird speed measurement, but that's what we get for using Australia math. Meters per minute. So student A walked 50, is that what we decided? 50 meters per minute? Meters per minute. And student B walked 20 meters per minute. That's average. And the way we did average was we figured out what the total distance was covered and the total time, and then just divided those two. That averages out their speed. Yeah. Assuming student A and student B walk at these speeds to complete the 2-kilometer trek on the field, how many minutes longer would student B take than student A? So, okay, so we have to think about how many meters are in a kilometer, because we need to figure out how, so we're using their average speed that we just figured out. And I'm gonna have to double check this. Kilometers, meters in a kilometer is like that, is that 100? Hang on. Oh, 1,000. So 1,000 meters are in a kilometer. So if they're doing 2 kilometers, they're trying to go 2,000 meters. So student A would take, if they're doing 50 meters per minute, you would do 2,000 divided by 50 to see how many minutes it would take them. I will do that in a second. Then student B, do I have room over here? No, I'm gonna do it over here. Student B, 2,000 meters and 20. I can actually do that in my head because those cancel, and they would take 100 minutes. And 2,000 divided by 50 is 40. And it's asking how many minutes longer would student B take than student A. So the difference between these are 60 minutes, so it would be an hour. 60 minutes. Hang on, that was messy. 60 minutes or 1 hour. So that's how much longer student B would take than student A. Okay, just making sure there's no more. Okay, that's the last question. Do you guys have any questions on anything? That was your homework assignment. So so hopefully you're able to complete it with me. If not, just go back and do it. Feel free to look back. I will upload these, like the answers, kind of onto Canvas and also this video. So if you need to go back, I will also link our original notes to this on this topic, the interpreting graphs notes, just in case that might help you. Yeah. Okay, I might hang out for a second just to see if you have any questions, but if not, you're free to go. 99 pages. You need one more page. Maybe I'll have to make sure next notes are only 1 page for you. Also, there are 6 of you on here, and I only have attendance for 1, 2, 3, 4 of you. Fiza, Jeanette, Eddie, and Sage. So if you haven't put your name in the chat, please do so I can take roll for you. I give you extra credit for being here on the live stream, so. Okay, sounds good. Well, you guys have a good rest of your day. I will probably have a study session today. If you want to join me, I will post a link on Google Hangouts. Remember that your 9 or J-1 is due today at 5, so if you're having trouble with it, I can help you on that one. Um, and yeah, have a good rest of your day. Hopefully, I'll see you in the chat and um, in the study session. But if not, enjoy your day. See ya.